Okay, in this video, we're going to explain how to project one vector onto another. So we have two vectors u and a, and we're going to express u as, here's this vector u, as a sum of two vectors u1 and u2. These two vectors u1 and u2 are going to be orthogonal or perpendicular, and the other property they have is this vector u1 is parallel to the given vector a, this other vector a that was given. It's going to be the direction that u1 is in, or the opposite direction, but in any case, parallel to a. Okay, so what are the formulas? Well, here they are. It's a little difficult for me to remember these, but whatever. u1 is equal to the projection of u onto a. This is just notation, or another way of saying what u1 is. And here's the actual formula. It's, you take the dot product of u and v, so that's a number, divide by the norm of a squared, that's another number. And so this whole thing is going to be a number, and then you multiply that number or scalar by this vector a to get a vector a, to get this vector u1. And what we see here is that this vector u1 is definitely in the direction of a because it's a multiplied by a scalar. So this formula certainly agrees or has this property that u1 is parallel to a. And then u2 simply is u minus u1. Since we want u to equal u1 plus u2, then we must have u2 is equal to u minus u1. And here's the first formula above for u1. So using this, we can find the formula for u2. I'll do an example in a second, but let me just give the proof. So again, I'm just proving where this formula coming from. So the starting point is u1 is equal to some scalar multiple of a. That's because the property of u1 is that it's parallel to a. So it needs to be a scalar multiple of a for some scalar k. That scalar is going to turn out to be this, but we don't know that just yet at the beginning of our proof. Okay, so then since u is equal to u1 plus u2, assume we somehow have these vectors u1 and u2. Well, then u2 has to be u minus u1. Okay, fine. And then the other property we have is that u2 is perpendicular to a. And here's where the dot product comes in. Because perpendicularity is easy to detect by the dot product, namely the dot product is 0, this means that u2 dot a is equal to 0. Again, what we're trying to do is find what exactly this value k is in terms of just the two vectors u and a that were given out at the outset. Again, here is going to be our final answer, but pretend we don't know that just yet. All right, so we've got u2 dot a is equal to 0. That's because u2 and a are perpendicular or orthogonal. That was, you can see from this picture here, we want u2 to be in the orthogonal direction to a. Okay, then u2 is u minus u1. Then u1 is some scalar multiple of a. And then in the next line, I distribute a to get u dot a is equal to, subtracting k times a dot a. The dot product of a vector with itself is the norm of the vector squared. And then doing some algebra of adding this term to both sides, we get this. Dividing through by this number, the norm of a squared, we get that k is equal to the dot product of u and a divided by the norm of a squared. That's exactly what was written here. And so our final answer is that u1 is, recall that was k times a, and now we finally figured out what k is. It's this thing. And then, so again, this is a number, and then multiply that number or scalar by this vector a, and that will give you u1. Finally, u2 is u minus u1, where here's the formula for u1. So that was a bit maybe abstract with lots of letters floating around. Let's do something with numbers. Here's an exercise from Nicholson. I'll just do part A. So it says in each case, write U as U1 plus U2, where U1 is parallel to this given vector V, and U2 is orthogonal to V. Orthogonal, again, means same as perpendicular. But okay. So the U1 is parallel to V. So U1 is a projection of U onto V. That's given by this formula from the previous slide. And so we just have to take the dot product of U and V. So in this example, V is what was previously denoted by A. Okay, so U and dot product with V is 2 times 1, -1 times -1, and 1 times 3. Add them all up, and you would get 6. That's the numerator here, U dot V. The denominator is the norm of V squared. So you take 1 squared, -1 squared, 3 squared, add them all up. To get the norm, you would take the square root, but here we have the norm squared, so we don't have to take the square root. And so we get the scalar simplifies to 6/11. So that's 6/11 times the vector V. The vector V is, well, if you write it as column vectors, it's given by this, just to save space. People also typically write it as the vector like so with round brackets. And so this is a scalar times a vector, and that means you have to multiply each component of that vector by the scalar. So we get this. And this is our final answer for U1. Moving on to U2, well, that's just U minus U1. The vector U is 2, -1, 1. The vector U1 we found here. And so we just do the subtraction. Subtraction of vectors is done component-wise. So, well, first of all, I just made a common denominator over 11. And so 2 is 22/11. Then subtracting off the 6 over 11. 22 minus 6 is 16. -11, you have to be a little careful about the signs here. -6 and then -6 there is +6. -11 plus 6 is a -5, and so on. Anyway, we get this as the final answer for U2. Okay, so yeah, what we've done is expressed this vector U as a sum of 2 vectors. This vector U1 is in the same direction as this. And then the other one, U2, is U minus U1.